In the previous video we were looking at dark matter. We also need to look at dark energy. And before we do talk about dark energy, let's just first of all link back to why we have a problem that dark energy might solve. And that is the fact that evidence suggests the universe is expanding at an accelerated rate. So if we consider all of the usual cosmological processes that we observe, we would expect that the acceleration might actually possibly be slowing down, or that it's a fairly constant expansion. But what we actually see from observation is that it's accelerating, and our current understanding of cosmological principles can't really explain that. So that means that because our current models, our current theories, don't actually explain the observations, we need to adjust those theories. And one of the possible solutions to helping explain that accelerated expansion is the existence of dark energy. So it's been hypothesized that dark energy could explain this expansion. Now, what exactly dark energy is, again, that use of the word dark indicates that we don't really know what it is, and so we need to sort of continue to do experiments, observations of the universe to get a better understanding of it. Basically, at this stage, it's an unknown form of energy that sort of acts in the opposite direction or opposite manner to gravity. So whereas gravity pulls things back together, dark energy seems to have the opposite effect and causes things to be moved apart. And as a result, that would then cause the accelerated expansion. So we have this solution to an observation that we can make. If we think about some of the evidence that we've been provided about this, the European Space Agency has a telescope, or a space observatory, I guess is the better way to describe it. It's known as the Planck missions, so named after Planck. So provided data that gives us an indication that most of the energy and matter in the universe that we can see, or that we have evidence of, is going to be made up of dark energy. So it's around 68% of the universe consists of dark energy. And just to sort of round out the picture, the remaining amounts would be about 27% of dark matter, and only around 5% of normal matter. So most of what we can see in the universe is actually only a very small proportion of what is out there, and we need to continue observing the universe, continue making measurements in order to get a better sense of exactly what dark energy is, and how it ties into our theories, and then adjust those theories to better account for what this dark energy, and for that matter what dark matter is as well. The last thing we need to cover in the option topic for HL is anisotropies in the CMB. Now I'm not going to go back over the CMB in any great detail here, because we've already covered that in D.3, but just to briefly summarize, we saw that the CMB is essentially isotropic. And again, that idea being that it looks the same in all directions. So it doesn't matter which direction you look, there's the same sort of observations that you would make. But if we take that a little bit further, there are actually some fluctuations. And by fluctuations we mean that it's some regions of space that appear to be a little bit different to others. And these fluctuations are known as anisotropies. They were first discovered by back in the early 1990s, and it was the Cosmic Background Explorer was the observatory that or the telescope that identified these anisotropies. So that was COBE, and as I said, in the 1990s, early 1990s. Since then, there have been a couple of other observatories that have been launched into space that have provided greater resolution, and those two that you need to be aware of were one was a NASA mission, first of all in 2001. So this one is known as the Wilkinson Microwave Anisotropy probe. So that's shortened to WMAP. And then in 2009, by the European Space Agency, and that one was the, we've already mentioned this one being the Planck Space Observatory. So with those two, we were able to then identify low-level temperature variations. These fluctuations in temperature are thought to be providing evidence of something that happened in the early universe. So thought to be the result of tiny random variations in the early universe, and in particular the density. So shortly after the Big Bang, some variations in the early universe that have then persisted and now being evidenced in the cosmic microwave background, and in particular in the anisotropies that we can see. Now, if we think about the evidence that we're talking about here, generally known as the Planck sky map. So there's a few images of this in the text, and a couple of things to identify is that it shows a lack of symmetry in the hemispheres or more specifically in the opposite hemispheres of the sky. There's also a cold spot, or a few different cold spots. We'll have a look at what those regions look like in a second. So a cold spot larger than previously shown by WMAP. So this is the sky map from Planck, and if we consider sort of the top to the bottom, you can see that there are some slight differences. So while it does generally look somewhat evenly distributed across the board, there are some slight variations in there. It's not quite symmetrical as we identified earlier, and the particular cold spot that we're looking at is this region down here, so a bit larger than what it was detected by WMAP. But you can see there that there are some regions where we get some sort of hotter patches and then some other colder patches. So the fact that cosmic microwave background is considered isotropic may not be a particularly valid assumption. Now, the last thing to mention here is that dark matter and dark energy have both already been incorporated into cosmological models. So we have had to adjust our understanding of what's happening in the universe. So those aspects have been added to the standard cosmological model. And with the recent evidence that's being provided about anisotropies, that evidence may actually require even further modification. So you can see that our understanding is not a complete one, and it's constantly being developed as further and more detailed evidence is provided, and it's the reason why we continue to send telescopes up into space to make more sense of what it is that we can see around us, and the models that we can use to describe those observations.